Hi, my name is W. Kent Tabiska, and I'd like to share work that we're doing on a topic called machine learning enabled thermosphere advanced by HASDM or META-HASDM. The main thing to remember, first of all, is that low Earth orbit objects will triple in the next 2 years, and that means that collision hazards will increase. Our META-HASDM work leverages existing accuracies of the US Space Force's High Accuracy Satellite Drag Model, or HASDM. We will significantly reduce uncertainties in the thermosphere's density specification to serve operations, conjunction assessment for global space traffic management. In particular, META-HASDM is going to provide these capability areas. We'll be able to provide comparative densities and thus creating ensemble uncertainties for operations using machine-learned algorithms. We have an absolute atmosphere density at HASDM's current uncertainty of 2 to 10%. The global density prediction will be enabled outside of HASDM's historic 20-year time frame. LEO ballistic coefficients will be improved about 500 kilometers. We'll also be able to dynamically calculate current epoch HASDM JB 2008 and forecast drivers, uncertainties, and finally, we're improving the solar and geomagnetic indices forecasts. Now, the primary customer of this will be the US Space Force Organization of Combined Space Operations Center, CSPOC. This supports command and control of space forces. The CSPOC HASDM Astrodynamics Workstation currently runs the HASDM code in order to create the current epoch and 72-hour predicted thermosphere densities. It's used to continually update the NORAD satellite catalog several times a day, and we will be able to improve the absolute error in HASDM without modifying the operational code at Space Force. In phase 1, we're developing new information that will be passed on as added metadata lines in the jbh.sgi.txt files that are delivered several times a day by us to CSPOC. In particular, HASDM historical absolute uncertainties will be provided representing satellite densities. The solar and geophysical indices forecast of historical absolute uncertainties will be compared with data. We'll be able to better provide solar S10 and F10 indices forecast using the Air Force's ADAPT model output. And finally, we'll have statistical uncertainty from the HASDM ML routine. Just like to finish up by pointing out that we have two general objectives in phase 1. One's a technology feasibility study with some main elements. The other is a science feasibility study. In the technology feasibility study, for past, present, and future, we have a number of tasks going from this SET HASDM database of densities through several different models. And those uncertainties in particular will be transferred over into the forecast to understand better what the forecast uncertainties are. In the science side, we will be looking at the oxygen helium transition at about 500 kilometers and above that affect ballistic coefficients. The carbon dioxide and nitric oxide cooling in the lower thermosphere is important. It's not yet modeled, and we'll look at that. The coronal hole high-speed stream effects are relevant to densities. And finally, DST magnitudes and arrival effects for geomagnetic storms and the solar far side evolution of our radiances will be looked at. So in general, I think that's kind of what we're looking at. I'd be happy to entertain any questions. Thank you.